So this is, as I said, this section is on characteristics of a good measurement system. Okay, so what is a measurement system? Well, you can think of a block diagram like this. A transducer, and tell what it is, a signal processor, and then a recorder. So a transducer is a device which basically takes some physical quantity, let's say distance or moisture level, and converts that into a voltage signal so that it can then be processed by the measurement system, which usually voltage is noisy, and so you need to do some post-processing in order to improve on it. And then that signal is your output, which then can be recorded to either in a SD card or in some other format. So this is the input to the signal processor, and this is the output. And here we are interested in the characteristics of this block, signal processor. Okay, this part, the first part, transducer, is actually a sensor, and we'll talk about this a little bit later. So a good measurement system has the following characteristics. So characteristics of a good measurement system. And we'll go through each of them today. Number one is amplitude linearity. Number two is adequate bandwidth. And the third one is phase linearity. Okay, so we'll go through each of them next. Okay, let's talk about amplitude linearity first. So if you make a plot of the measurement versus the input, they should be pretty much 1:1, or in the sense they should be linearly dependent. So let's say that this is the input. It is some signal which has two ramps like this. Ideally, you want to have the output to be something like this. This is the output. This is the input. So if you take the ratio of the output to the input, it's more or less a constant. Okay. A good measurement system will do this, which is really nice because now you can easily relate the output to the input through this constant. Many times you'll see that the input is of the order of few milliamps or like millivolts, but the output is typically, you would like to have it in the order of volts because it's much easier to measure something which is bigger. So, the other thing which we'll be talking about later on is amplifying the input so that it can be measured by the system which you're using for measuring. Now, what happens in reality is that However, in real systems, we see the following two things. The ratio above is constant only for a range of input amplitudes. That is, you can only guarantee this for a certain inputs, and if the input is beyond that range, then no longer the output is linearly related to the input. The other problem, which will also be coming up, which is part of number 2, which is bandwidth, is the ratio is constant only for a certain range of input frequency. So you cannot use this device at certain frequencies, and you can use it for some others. So that's another thing which is important, which actually gets us to the second point, which is bandwidth. So 2 gets us to bandwidth, which is probably the most important thing in this section, and this will be part of your lab. Okay, so let's talk about bandwidth. Okay. Before we talk about bandwidth, let's talk about Fourier series, which is very central to measurements. So Fourier series representation of signals. Okay. So any the Fourier series says that any periodic waveform can be represented using a infinite series of sines and cosine. Okay. So any periodic waveform can be represented as a sum, as an infinite series of sines and cosines. Okay, so what this means mathematically is that if f of t is periodic, some periodic function, then you can write it as follows: t0 plus the summation n equals 1 to infinity an cosine n omega zero t plus bn sine n omega 0t. Okay, where the sum, the infinite series, is here. Infinite series. And then sines and cosines are shown there. Now, the values A's, C's are constants. Bn are constants. Okay, so they can be found, as I'll show you, I'll write a formula. And then omega 0 is also called as the first harmonic. It's called the fundamental frequency or the first harmonic. Or first harmonic. Okay, or in other words, the lowest frequency in the periodic waveform. Okay. So omega is actually related to the time period by this formula. So if you want to do the time period, you just use this formula. If you given the natural frequency omega 0. So let's see how to compute an, bn, and c, which are constants. Okay, c0 is nothing but 1 divided by t, the integral from 0 to t, f of t dt. C or a n is two divided by t, the integral from 0 to t, f of t cosine n omega 0 t dt, and bn equals 2 divided by t, integral 0 to t, f of t sine n omega 0 t dt. So if you use this formula, you'll see that c0 is nothing but half of a0. You can just put omega n equals 0 and then see that this relation is true. So you don't really have to evaluate c0, it's just a0 divided by 2. Okay. Now let's see an application of this. If you are told to compute the Fourier series of, here's an example, and I won't be expecting you to do this computations. I just want to you to get some intuition about this. This is kind of very fundamental about measurement systems. So let's say that we have control or a measurement which is something like this, 1 or -1, depending on what the time is, 0 to t divided by 2 and t divided by 2. Now I just wrote down the only one time period from 0 to t, but this is a periodic signal, so it just keeps repeating itself. Okay, so what does this look like? It will look something like this. Say 1. And -1. Okay, so from 0 to t divided by 2. So let's assume that this is t divided by 2. It's t. This is 2, 3t divided by 2 and so on. Then the signal will look something like this. So it's 1 from 0 to t divided by 2. Then it goes -1, and then it goes +1, and just keeps going that way. So now this signal is periodic, and then we want to now try to compute this as a sum of infinite series of sines and cosines. So you can do that. You can use this formula, which I wrote down earlier. And I said, I'm not expecting you to do this even for homework. It turns out that an equals 0 equals c0, and bn equals 2 divided by n pi, 1 minus cosine n pi. Okay, so once you have the coefficients which comes from integrating this expressions, then you can write the function f of t now as a infinite series using the formula I wrote down earlier. N goes from 1 to infinity, 4 divided by 2, n minus 1 pi times sine 2n minus 1 omega 0 t. Okay, so this is so don't worry too much about the calculations, but this is where I want you to pay attention. This is the interesting part. Let's say that of this infinite series, we only chose first term. Only first term. So n equals 1. Okay, if we do that, then you can put n equals 1 here. You see 2 minus 1 is 1. So this will be something which looks like a sinusoid. And this will look just a sinusoid. So if you look at this signal and then you look at the original one, you'll see that it doesn't quite look like a sinusoid, right? So clearly that first term does not capture everything about this series. Now, if you take the sum of the first three terms, that is, you put n equals 1, 2, 3, you go to the sum up to 3, then you'll see that it looks something like this. Okay, which by the way also doesn't look like what we have. Let's do sum of pi terms. First 5 terms, n equals 1, 2, 3, 4, 5. Now it will start looking something like this. Okay, and then if you do sum of all terms, clearly you will get the original signal, which is okay. So you can see that as I keep adding terms, the accuracy of my of the curve becomes better and better. So many times you don't really need to show all the terms. You can truncate it. Like this is, I would say, fairly close to this, except for that for this part, it looks fairly close. So maybe you can just truncate it at 7 or 8 terms, and you just are able to recover the signal. Now, let me just take the same signal and just add an offset to it. So consider the same signal with an offset. Okay? So you'll learn about offsets and specifically how you can put them using a function generator in one of the labs. So I think that would be the lab, which in this particular lab, which will come in 2 weeks. So what we do here is we offset the voltage by 1.5 units. So we just shift it up by 1.5 units. So this will look something like this. So the 1 is 1, 2, and this is 2.5. So the 1 will be, if you have to add 1.5 to it, so it will become 2.5. And since the -1 gets 1.5 added, it becomes 0.5. Again, it keeps going so on. Now, for this one, you could also do the same thing, do what you know as the Fourier series. And you can write the Fourier series, but here what we're interested in is making a different plot. So look at the Fourier series, and then we try to find the amplitude. By the amplitude, I mean those coefficients, the A's and the B's, as a function of frequency. And then you will see that at a frequency of 0, the value of 1.5, then we would have at the fundamental frequency omega 0, something like this. Yeah, so these values are omega 0, 3 omega 0, 5 omega 0, and so on, 7 omega 0. Okay, so you're making a plot of amplitude versus frequency, and we get this. We come to know that at a frequency of 0, the frequency of 0 means the constant part of the signal, which is basically the offset here, has an amplitude of 1.5. This is basically saying that this is 1.5. That has the biggest amplitude. And then if you look at the amplitude of the component which has frequency omega 0, that is the next biggest one, and then it keeps decreasing. So this is basically making what is known as a so-called, similar to what I'll introduce, it's called a Bode plot, which is plotting the amplitude versus frequency. It basically gives an idea of the frequency component of the signal. It's telling me that the biggest part in the signal is the constant part, and then the fundamental frequency is the next one, and so on. And so you see clearly as the frequency increases, the contribution decreases, which means that for this signal, if you use the first few terms, maybe the first 4 terms, then you'll get a faithful representation of the signal. You really don't need to go beyond the 5th frequency. That's just like what I showed in the earlier plot. Okay, so this gets me to the part on bandwidth. Okay, so the bandwidth, we like to write this in terms of dBs. It's 20 log 10 A out divided by AN. So A out divided by AN are the ratio of the amplitudes, like we wrote down earlier. And then dB is our unit to measure the ratio of those two amplitudes. It's the logarithmic log of the ratio of the amplitudes. So this is decibels, and this is the ratio of amplitudes. Okay, so what we're trying to do here is this. We are trying to make a plot of the frequency on the x-axis to the ratio A out divided by A. Okay, so you know the measure, if you know the inputs, you know the outputs, and you know the frequency at which the frequency is the frequency applied to the input, then you can make a plot by choosing different amplitudes, ratios. And let's say that the plot looks like this. Okay, so there are 2 points of interest. One is this point where the ratio is 1, and then there is another point which is 0.707, which actually is 1 over square root of 2. This corresponds to a dB of 0. So if you put the ratio A out divided by N equals 1, you'll see that log 10 is 0. And then if you put 0.707, then you'll see that this dB is -3. The bandwidth is defined as the frequency at which the amplitude ratio is between is -0.3. Okay, so if this is the lower frequency, this is the higher frequency, then this is the bandwidth. Okay, in other words, remember I told you that one of the desirable characteristics of a measurement system is that the ratio should be constant. In fact, the bigger the number, the better it is. But in this region, you can actually get almost 1, which means that your measurements are going to be good, and anything below that, it's kind of shaky. The measurements are not so accurate because the ratio quickly falls down below a ratio of 1. So this plot is known as a Bode plot. This is one part of the Bode plot. This is just plotting the amplitude versus the frequency. The other one is the phase. We'll not talk about the phase so much in this class. So the bandwidth definition is range of frequencies where the input is not attenuated by more than -3 dB. So in what that means, as I said, is that where you can faithfully trust the measurement system is only in this frequency, in the bandwidth, where you can trust the measurement system. So the higher the bandwidth, the bigger it is, because the bigger range at which you can trust it, and the smaller one it is, the poorer the system is. Okay, now let us look at an example where we compute the bandwidth of an electrical system. This is not strictly a measurement system. So here's an example. Okay, so consider this system consisting of a RC circuit, so R and C. And let's say that we supply it with some input and we are measuring the output across the capacitor. And the question is, so plus negative, compute the bandwidth of this circuit. Okay. So in order to do that, what we need to do is we need to relate the output to the input. Once we have this ratio, we can then compute the bandwidth. So let's use what we've learned in the previous class, which is we'll convert this capacitor and resistance to basically impedance. So this is XR, which is simply R. And then for the capacitor, it is XC, which is minus J omega C. Okay, now once we have this, we can now use our what do you call, the voltage divider rule. If you want to find the voltage out, it's the ratio of XC divided by XC plus XR times V in. So if you want to find V out divided by V in, it's XC, which is minus J omega C divided by minus J omega C plus R. And so in order to simplify this, what we do is we multiply with the complex conjugate of the denominator, which means that we need to multiply with this plus J omega C plus R, and then same thing up. This is just a trick used to convert something which has a J, or the complex number in the denominator, to a real number. So when you do that, you get V out divided by V in. Just carry this. Copy. Okay, let's do this math, but I've not done it here in my notes. V out divided by V in equals J square is -1, so it's positive. So omega square C square plus minus J omega CR divided by omega square C square plus R square. Okay, let's divide throughout by omega C. So omega square C square, so 1 minus J omega R divided by, there's no just R divided by omega C, 1 plus R square divided by plus C square. Okay. Just going to check if the math is correct. Because C. Okay, now let's call this J omega C omega divided by 1 plus omega C divided by omega square, where I've defined omega C as 1 divided by RC. Okay, and then you can actually show that V out divided by V in is nothing but 1 divided by 1 plus omega divided by omega C square. Okay, so simplify to the simplest form you can possibly get, then do a plot of, just carry this forward. So we have V out divided by V in equals 1 divided by square root 1 plus omega divided by omega C square. So let's make a plot. Of V out divided by V in times omega. So what you can do is, first let's just put omega equals 0. So when you put omega equals 0, you'll see that it's 1 divided by 1, which is say this point 1. And then let's put omega equals infinity. When you put omega equals infinity, the denominator will become close to 0, right? So it will be, so if it'll be 1 divided by infinity, and then 1 divided by infinity is close to 0, so it'll tend to 0 as omega becomes bigger and bigger. So it's the curve starts here, it should go to 0. Now, what you need to do in order to make this plot is put a different values for omega. For example, omega equals omega C. If you put omega equals omega C, then you see that it comes out to be 1 divided by square root of 2, which is 0.707. So at omega equals omega C, we'll have 0.707. And then you can plot a couple of points, but you'll get a curve which looks like this. Okay, and the frequency can only be positive. So what we have here is this critical point, 0.707, corresponds to dB minus 3. And so this is going to be the bandwidth of the signal. So bandwidth is from 0 to omega C, which is 1 divided by RC. Okay. So that's the answer to the bandwidth. This circuit is actually used as a circuit which will pass the lower frequencies, and it will attenuate the higher frequencies. So these are the higher frequencies. So if you have a sensor, like say an accelerometer, or even something which measures velocity, like an a gyroscope, it usually has high frequency noise. If you connect it to this circuit, that is the output of the sensor is V in, then your output will only pass the lower components. It will cancel off the noise in the signal, cancel the high frequency noise. So this is useful for most of the systems we see have this high frequency noise component, and so it's useful. Contrary to this, there is something called a high frequency filter, which basically attenuates the other half, which is it will attenuate the lower frequencies and will pass the higher frequencies. Actually, by that, it's called a high pass filter. This is the low pass filter, and you'll be doing these circuits in one of the labs, which is 2 weeks from now. Okay, the last thing which I wanted to say before we stop is the phase linearity, and I'm almost done. Phase linearity. Okay, so let's take the original signal, input signal. And let's say that this is the output. So output, okay, this is sine omega t minus p. This is input, which is sine omega t, and that's because at t equals 0, the amplitude is essentially 1. Sorry, 0 amplitude. Okay. Okay, so what is happening here is that at this basically corresponds to a delay in the signal, right? So when you shine in the input, you have to wait for TD seconds in order to see the output, which is actually bad because now your signal is delayed by a time TD. And imagine using this signal to do some control. It's going to not, the system is not going to be controlled well because of this delay. So the smaller the delay, the better it is. So this delay is related to the phase angle. So this is a signal which lags the input. Okay, it lags the input by a phase angle. P equals 2 pi ED divided by T. Okay, or sometimes people like to talk about the delay in terms of time, TD, which is absolutely fine. So if you're a person who deals the frequency domain, you look at the phase. If you're looking at the time domain, you look at the time. You can also write this in terms of frequency. Frequency is 1 divided by T. So the frequency can be written as 2 pi f times TD. In other words, the phase is usually proportional to the frequency, and this is what you would like to see. You would like to see phase linearity, which is the phase is dependent on the frequency. So if the phase is proportional to the frequency, then the system is good, and that's what you would like to get. And you'll obviously want to have a minimum delay as possible.